Okay, so hi everyone. Yes, I'm with Machiavelli Labs, and we're trying currently to leverage machine learning techniques for communication systems. And you all know already from what we heard today that machine learning has been revolutionizing field after field in the past decade. And that's why today I want to show you 3 examples of what machine learning can do also for wireless communications. And in particular, I'm going to focus on applications at layer 1 and layer 2 of the radio interface. So the first application I want to show you is called DeepRx. Now, DeepRx is a deep learning-based MIMO receiver architecture. Okay, you all know that conventional MIMO receivers have several building blocks inside, like equalizers, demappers, channel estimators, and so on. What we want to do is to replace all of those blocks by machine learning models. So yeah, how do we do that? We have designed DeepRx as a ResNet-based convolutional neural network. And why do we use convolutional neural networks? Well, we focus strongly on OFDM as the transmission mechanism. And if you look at the physical channels of OFDM transmissions, you know they are all highly correlated in the time and frequency domain. And by using convolutional neural networks, we perform also bidimensional convolutions over this whole time frequency dimensions. And it is precisely, this access to both dimensions what lets DeepRx find the correlations that exist between nearby resource elements in the time frequency grid. And this is pretty advantageous for channel estimation purposes. If you look at if you're familiar with OFDM, you know that not all of the resource elements in an OFDM grid carry data. This grid is punctured, and there are so-called pilot transmissions or reference signals that are used to sound the channel, right, to get an idea of if the channel is good or bad. And what we do by using convolutional neural networks is we perform a correlation analysis on the whole grid that lets us extract information not just from the pilot carrying resource elements, but also from the data carrying elements. So basically, we're exploiting everything that is known from the transmission by looking at this OFDM grid. And yeah, the result is that this produces receivers that are highly tailored and customized to the channel where they have been deployed, as well as to the hardware where they run. And yeah, this pumps up performance in a nearly hands-free fashion. If you're interested in more details, there's a bunch of papers on the topic. So here you can see the tasks that DeepRx acquires. And I guess you could consider this as kind of the first assault of machine learning onto the physical layer. And of course, we could be more ambitious and try to incorporate more responsibilities into DeepRx, but the fact is that there are some blocks already that we have at the physical layer that are pretty effective and pretty cheap. If you look at FFT, this is something we've been doing for years, if not decades. It costs nothing to produce, so there is the motivation to try to do FFTs with machine learning. And some other blocks are just trivial, like the removal of the cyclic prefix, so we certainly don't need machine learning for that. Now, having said that, that doesn't mean we could not aspire to have to get rid of all the signal processing blocks and just have one huge neural network that does all of the physical layer processing for you. This is, at least in theory, in principle, possible. Now, DeepRx is a convolutional neural network with residual connections. Residual means that the connections between the layers in the neural network do not always link a layer to the next layer. Sometimes we skip some layers. And this is done for training purposes. This is a very common technique to avoid the so-called vanishing gradient problem. And it's also a very scalable architecture. It lets us, it's a design that lets us accommodate easily multiple MIMO streams. We have trained DeepRx to learn the so-called log likelihood ratios, or soft bits, in a given TTI of an OFDM transmission, and we use supervised learning techniques to train it. Here you can see some performance of DeepRx. This is our machine learning-based receiver. And I'm showing you the performance here in 2 channels. So we have TDL, by the way, stands for time delay line channel. And we have 2 types of channels here, TDL-A, which is a non-line of sight channel, and TDL-E, which is a line of sight channel. And by the way, DeepRx has not been exposed to any of these channels during training. Okay, so I'm showing these channels here just for validation purposes. DeepRx has been trained in different set of channels, but it nevertheless has learned to exploit channel knowledge and can accommodate and generalize pretty well to challenges it has never seen before. And yeah, this is, I mean, we try to do this for wireless communication systems, but this has application in other communication systems as well. Like I could imagine in optics, for instance, this is a very stable channel. So you could just, I don't know, if you have a very long fiber, you could just run the training across this fiber and just learn the heck of this fiber and come up with a very customized receiver just for this fiber alone. So yeah, so the second application I want to show you is called end-to-end learning. So now we don't just look up the receiver side. Now what we want to do is to train both a transmitter and a receiver to come up with the optimal constellation, the digital constellation, to communicate. Okay. Now most commercial systems today, they use some form of a QAM constellation for communication. And we typically use techniques like link adaptation to change the constellation order, right? If the channel is bad, we decrease the constellation order. If it's good, we add more symbols to the constellation. But we could ask ourselves if the CQI, this is the channel quality indicator, is the best and only indicator that we have that suggests that the constellation order a constellation order change is necessary. The thing is that when the signal degrades, this can manifest itself in many ways, and some of those ways are pretty subtle. Okay, we don't just need to look at the CQI. We could be looking at things like the block error rate, number of retransmissions, number of reconnections, the buffer sizes, etc. So how could we make sense of all of these data in order to choose the best constellation? This is the difficult thing. This is what we humans struggle to do. I mean, our link adaptation algorithms today, they're based on the CQI, which is very intuitive. Everybody can understand that, yeah, CQI is just a number between 0 and 15. If it's 15, the channel is good. If it's 0, the channel is bad. And in between is typically what you get. So this is intuitive to us. But the moment we have to work in a multidimensional space with all of those inputs, well, it's not that easy to come up with a good algorithm. That's why we turn to machine learning, which can make sense of all of this data. And what we propose is to train a machine learning model to build this constellation for us based on all of these inputs. And yeah, I must highlight that the constellation must, of course, be understood by both the transmitter and the receiver. And that is why we need an end-to-end model. Yeah, more references. Yeah, so this is the proposed end-to-end model. You see here I've highlighted some blocks in gray. These are the blocks that we train together end-to-end. And the objectives of this learning task are twofold. I mean, first objective is to be able to communicate without pilot overhead over a nonlinear power amplifier and a frequency selective channel. And the second objective is to produce a waveform that has low out-of-band emissions. Okay, and it's pretty easy actually to code all of those objectives into the training loss function. Here you can see some of the training results. I want to emphasize, by the way, the difference between the black and brown curves. I don't think I have a laser pointer here. Oh, yes, yeah. So you see here the brown curve would be the curve that we will obtain only with DeepRX, which is the technique I showed you in the first part of the talk. But the moment we actually train this end-to-end, we have all this decrease in the block error rate, especially in the highest signal regime. So this is what you gain just by introducing another convolutional neural network on the transmitter side. And yeah, and you also notice, by the way, that the system has learned a constellation that is quite extraordinary compared to the constellations that we're used to. The reason why this constellation looks so asymmetric is because the channel is not perfect. Channels in real life, they're not symmetric. So what our method has done is to learn the asymmetries in this channel and produce a constellation that is highly tailored to this particular channel. And it is precisely this asymmetry that what lets DeepRX correct for the phase and amplitude responses of the unknown channel. And this little animation shows you also the evolution of the constellation and the performance during the training process, and it gives you also an idea of the exploratory process in the constellation space. It also highlights, I think, the asymmetries that you see in the channel. Okay, so now I'm coming to the third application I wanted to show you. Now I'm coming up one level in the protocol stack, and I've shown you how to train machine learning models for the physical layer. I want to show you now how we can also train a machine learning model to learn a MAC protocol. So yeah, the first question is, how are protocols made? Okay, so today, protocols are agreed at the industry, at an industrial level, right? It takes months, if not years, to develop a protocol. With high cost, this comes with high cost. Typically, I don't know, at 3GPP, we send all of those delegates to the meetings where there are all these technical discussions, whether to include a new bit into some message, and this often gets entangled with technical and also commercial discussions. But we think that it should be possible to accelerate, automate, and optimize perhaps this process. Okay? It doesn't need to take that long, and we think we can do that with machine learning. We think machine learning is a appropriate tool because protocols, if you think of a protocol as the language between two machines, we know that languages are learnable. We humans, we have learned languages. And in the same way, we'd also learn protocols. Okay? Just to put you an example, if you look at a base station and a telephone, before the telephone can send the first bit of useful information to the base station, your telephone needs to have a conversation with the base station. Okay? They both need to agree on the time frequency resources that you're going to be transmitting on, the power of the user equipment, the modulation encoding scheme, and many more things. Okay? This exchange is dictated by the protocol, and it's once again a language. It's an exchange, a conversation between those radio nodes that set the conditions for the transmission to take place. And yes, and since we know that languages are learnable, and there's also already a large body of work on machine learned languages, we think we can reuse this to try to learn a protocol. So that's kind of the gap that we're trying to bridge. So if you think of the MAC layer, especially the archaic MAC, okay, so the first MACs that were deployed for wireless systems, they had two main responsibilities. The first one is the scheduling of the transmissions from multiple UEs. Okay? The MAC layer has to take decisions to map radio resources to the users. And the second objective, the second responsibility of the MAC layer is to communicate those scheduling decisions to the users themselves. In other words, the MAC layer has to solve the multiple access problem. And at least that was originally the plan. Today, the MAC layer does many more things, and most of those features have nothing to do with multiple access. They're just there in the MAC for speed reasons. Okay, so the MAC is a fairly low layer, it's close to the physical layer, it works at high speeds. So those features profit from this performance of the MAC layer. And in recent years, we have seen multiple efforts to try to apply machine learning to these features. Okay, so if you look at any of these MAC features, you will find tens, if not hundreds, of papers trying to do machine learning. So there's machine learning for scheduling, machine learning for time in advance, for DRX, for paging, you name it. Any MAC feature you can identify, you will find machine learning papers for that. I like to call this way of applying machine learning to MAC features as MAC feature learning. Okay, we do machine learning for a MAC feature. But as you see, all of these features still have to play by the rules and the constraints of the control plane, which, by the way, does not look like this very nice single block. Instead, the control plane looks pretty much like this. And yeah, so perhaps you have, I don't know, a pretty amazing and new novel DRX algorithm that could use maybe information from the battery status at the UEs. And you want to deploy this new algorithm. Well, too bad, because, for instance, today in 5G, the standard, the MAC standard, does not support the transmission or the exchange of UE battery information status. So what if you have a customer that could really profit from this algorithm? Maybe your customer is, I don't know, maybe your customer has battery power cameras. Those are the UEs of your customer. So you really want to deploy this new algorithm. Well, what you could do is to change the control plane. And as a matter of fact, 3GPP changes the control plane on every release. But do we need to wait several years for this to happen, or can we accelerate it? Can we do this faster? And it turns out that the control plane is also learnable. And so are other parts of the MAC, like, for instance, the data path. So if you want, it's conceivable to think that you could end up learning the MAC feature that you're interested on together with the signaling and the data path it needs to provide the results you desire. And if you are more ambitious, you could even try to learn multiple MAC features jointly with the control plane as one unified MAC learning model. So what are the standardization implications of learning this control plane? I mean, I don't think this means that we don't need industry-wide agreements for cross-vendor compatibility, which we do need. But I think it suggests that we might be able to automate the way in which we reach some of those agreements. Okay, so and if this idea materializes, I think we might see a shift from standardization efforts, from standardizing bits and messages, fields, messages, and procedures, to standardizing things like training enablers, testing procedures, system requirements. Okay, so how do we do this? How do we train a protocol? Here, just for simplicity and just focusing on one MAC feature, which is scheduling. And we want to learn this feature together with its associated control plane. And what we do is we model this MAC feature as a reinforcement learning agent with two action spaces. Okay, so this reinforcement learning agent has a downlink signaling action space plus a user plane action space, and it also has access to observations. These are contextual information that is available at the base station side. Things like the states, the RRC state of the UEs, the mobility configuration, the history of past sales, and so on. And the training objective, the training task, is to learn how to map those observations to the optimal actions. And by the way, we should not forget that we don't just need to train the base station. We also need to train all of the UEs. So this is, in a way, a multi-agent problem. And that is why we need a multi-agent reinforcement learning algorithm, or MARL algorithm. So the next step is to define what you actually want to optimize. Here, just for simplicity, I'm just formulating this as a bitrate maximization problem, but you could try to maximize things like energy efficiency or some multi-objective combination of them all. And the next thing is just to choose appropriate training algorithm for this. We use one multi-agent reinforcement learning algorithm called MADDPG, which stands for Multi-Agent Deep Deterministic Policy Gradient. That's a mouthful, but it's a pretty effective algorithm that exploits information from all of the agents at training time. And this is done in this central training platform. But then you can deploy the algorithm, you can get rid of the training platform altogether, and these agents will have been trained to learn and perform very effective protocols. And this performs pretty well. We have seen that we can train protocols that beat contention-free baselines, at least in very small scenarios. It trains pretty fast, and it's also pretty generalizable to scenarios never seen during training. But many challenges still lie ahead. I mean, the first one is the scalability. We are struggling to train these protocols in larger scenarios. And then there's also the question of interpretability. We have trained some protocols that show behaviors that were, at least to us, a bit unexpected. I've seen protocols do things that I've never seen in human design protocols. Just to give you an example, most human design protocols are based around the idea of an acknowledgement. So you send a packet, and then the receiver sends you an acknowledgement confirming that it has been received. This notion also exists in the protocols we have trained, but the agents we have trained know that sometimes they can just ignore the acknowledgements altogether, and other times they should rely on them. And this increases performance a lot. So and this is just, since I'm out of time, just a summary of the main motivations for this work. I think with machine learning we can customize these protocols to particular scenarios. We will train those protocols for performance, so there's no human factor involved, no commercial considerations here. It's an automated process, so we don't need to wait 1 year for a team of engineers to develop the protocol. We can just click train, and it will do it for us. And finally, there's a scientific motivation to explore this very vast space of protocols that we don't know about. Yeah, thank you.